Hello and welcome to a special Optica Industry briefing and a brilliant guest I want everyone to meet. On December 13th, physicists from the National Ignition Facility at the US Lawrence Livermore National Lab in California announced a breakthrough in the race to recreate nuclear fusion. But how long before this clean energy source powers homes, and what role can modern lasers play? To discuss this breakthrough in more detail and understand what it means for the photonics industry, I'm joined on the line by Michael Campbell. He is the former director of the Laboratory for Laser Energetics in Rochester, New York, and he's been involved in laser fusion from the start. But first, let's recap on what's been announced.
There's a tiny cylinder here at the end of this that you probably can't see. It's about so tall and this wide. Inside that was a small spherical capsule about half the diameter of a BB. 192 laser beams entered from the two ends of the cylinder and struck the inner wall. They didn't strike the capsule, they struck the inner wall of this cylinder and deposited energy, and that happened in less time than it takes light to move 10 feet. So it's kind of fast. X-rays from the wall impinged on the spherical capsule. Fusion fuel in the capsule got squeezed. Fusion reactions started. This had all happened before, 100 times before. But last week, for the first time, they designed this experiment so that the fusion fuel stayed hot enough, dense enough, and round enough for long enough that it ignited, and it produced more energies than the lasers had deposited. About 2 megajoules in, about 3 megajoules out, a gain of 1.5.
Thank you, Mike, for joining us today. Where do we start?
Yeah, well, first of all, a little bit of my background. So I've been involved in this field for lasers and fusion and their applications for over 45 years. I began my career at Livermore, and I was the one who initially started the NIF project, sold it to Congress and the government. And so I'm very happy to see that it has achieved what we said it was going to do. I've recently retired from the University of Rochester, the Laboratory for Laser Energetics, which is the largest academic institution working on laser fusion, high-powered lasers. I retired there in March of this year. So I still stay active in the field. I talk with everyone involved in the research, the startup companies, the laboratories, and so that's my background. I still am committed to seeing fusion come to our world one of these days. So what happened last week was a very, very important event in the scientific advances for fusion. It was the first time ever that the fusion output from an experiment exceeded the energy that was done to make it happen. So it's like my analogy is the Wright brother flyer in the US, many years ago in 1903. A plane took off for about 100 feet, showed that heavier than aircraft could fly. And this shows that the scientific underpinnings of fusion work. And my great compliments to the researchers at Livermore, those who operate and operate the laser, those who conduct the experiments, and the team not only at Livermore but working with them and making the targets. University of Rochester, Los Alamos, all the community. This is a great benefit for the community, but it really was a landmark event because it showed that we could make fusion in a laboratory on a scale that we can eventually make affordable. Now, some people say, this isn't a scientific demonstration. NIF was not designed as an energy source or an energy research program. It was a science machine, a science tool. And so this is science. So when you see some critics say, well, it took so much energy to make energize the laser, that wasn't the purpose. The purpose was to do the science. And now that that's been demonstrated, now we will begin to see and has continued to see a lot more interest in developing the energy and other applications of NIF. Now, remember, the reason why NIF was done was to ensure national security for the United States. We have not tested nuclear weapons since 1992, and we want to make sure that the nuclear deterrent, never to be used, but is there to make sure that everyone knows that it would work and be safe and secure. So that was a principal reason for NIF. But just like in many things that have developed for national security, like I don't use a map anymore, because of GPS, and GPS was there to make sure precision weapons. So we didn't have to drop 100 bombs to do one thing. So I expect we'll now see a lot of resurgence or interest in fusion energy because of this demonstration. But we don't forget the original reason for doing NIF.
So today you are talking to the industry network of Optica. We have 400 corporate members. Those are companies who develop either high power lasers, laser optics, detectors, assembly technologies, they measure the LIDT. How should we react as an industry association? What do you think is the benefit from this amazing result to the global industry network?
It's a very good question. There is enormous opportunities because laser fusion requires cost-effective, high-performance lasers and optical systems, and so the business of making diodes, that are both powerful and cheap, and large quantities is something which is going to be driven by this. Making optical materials, the gain materials and solid state, and even with gas lasers, is going to be very, very important. Optic industry, to be able to, not only make the light, but get it onto a target, is going to be very, very, very important. So I think there's tremendous opportunities for industry in all aspects, in making, high-powered lasers that are efficient, that are cost-effective, and in the end, there'll be many of these things. So I think the industrial applications are enormously, are very positive. Just like NIF. NIF required enormous involvement by industry to be able to make the NIF laser possible. One had to learn to make laser glass cheap and large amounts. One had to learn to grow KDP crystals fast and cheap. Many, many things that NIF had to have industry do before you could assemble the laser. This is the same thing happening here.
The experiment actually had 192 laser beams. I have been in the last week looking at different documentation, trying to find out some knowledge about power, wavelength, repetition rate. Is there anything you could share with us about any of these parameters? What do we call high power? What wavelength is the wavelength of choice? Is it 1 micrometer, or are we going into the mid-infrared? Are we talking CW, or are we talking about ultra fast? Is there anything that you could tell us a bit about the parameters that the laser industry should be prepared to deliver?
A very good question. So first of all, it is a pulse laser. So the typical laser pulse will be, say, somewhere around 10 to 20 nanosecond laser pulses. In that laser pulse, energy somewhere between 3 and 10 to 20 megajoules should be in that laser pulse. So the powers we're talking about are hundreds of trillions of watts. For IFE, NIF fires a few times a day. An IFE plant will have to fire anywhere from 80,000 to 1 million times a day. So we need to have rep rate. So this is something where diodes and being able to remove heat is going to be very important. Be able to keep the beam quality good. The frequency that you'll be using, over the past number of years, we learned that laser fusion works when the wavelength is in the ultraviolet or in the ultraviolet. So we not only do we have to make 1 micron lasers, we have to frequency up convert them into the ultraviolet, into the third harmonic and third harmonic. So as a minimum, nonlinear optics is going to also play a big role in this. Precision, the optics. I mean, to give you a sense, NIF has roughly 300,000 or 400,000 square centimeters of aperture. That's a lot of optical systems in that, but that's what we're talking about. It's the largest optical element ever made. And just imagine we need many, many of these things, and they have to be able to withstand not 1 pulse a day, but 1 million pulses a day. So I think there's going to be a lot of research done not only in fabricating optics, but also making them be damage resistant, be able to make them cost effective, and be able to make lots of them. So I think enormous opportunities for industry.
If we go to the UV, we are talking about the third harmonic.
Yes.
So what kind of nonlinear crystal do you have in mind? Would be the one that you think, okay, we need to look at gallium selenide, or is there any particular nonlinear crystal that you think is the one that we should be prepared for?
Yeah, so what is used routinely now is KDP, and that will probably be the material that people are using for these things as we do this. Now, of course, there's very good frequency conversion efficiency. We have to make sure that they don't get too hot, they don't absorb very much, was very good. but be able to fabricate them in the sizes and the time scale that you need is going to be very important. So nonlinear optics is a very important part of this. Same thing also, the laser pulse is shaped in time. So being able to shape the laser pulse efficiently in time, we've learned to do that, borrowing from the optical telecom industry and such, a lot of digital pulse shaping, machine learning to be able to make better pulses. So there's not only opportunities in industry, and I'll say the traditional laser and optics industry, but in the information technology industry, there's lots of opportunities there also. And just as important, making these little bitty targets. You have to make these, the targets for laser fusion are going to have to be done again, up to 1 million a day. And they have to be made for less than $1 a piece. And so, advances in additive manufacturing, making of foams of material that can be wetted with deuterium and tritium. So lots of opportunities across the spectrum.
For me, one of the things that was the most exciting is the 192 laser beams.
Yeah.
We need an amazing beam splitter. Is there anything you could tell us about this? Why 192? And do we need 192 individual lasers? I guess not. I guess there are ways to use some kind of diffractive optical elements to split the laser beam into 192 beams.
No. So there's 192 optical, amplifier chains, right? And so you have a master oscillator. Then you split it into 192 beams, and it gets preamplified and amplified separately in different beam lines. Now, future systems will be hundreds to thousands of beam lines working together, just like NIF does. And so NIF is, as you say, it's 192 laser beams, because you have to irradiate the target in special ways, right? You just can't shoot a laser beam on. You have to irradiate it so the implosion can be uniform and the like. And so there's different ways of doing that. So there will be opportunities for many beams. I've seen designs which are just a few beams, and I've seen designs which are 5,000 beams. And I think over the next decade, we'll be doing research to find out which one works best.
This is really exciting. You know what I like the most about the press conference on NIF? The moment in which it was said that even though the system had a gain of 1.5, the laser was not designed to be efficient.
I want to be clear, ultimately this experiment, as Kim mentioned, drew about 300 megajoules from the grid in order to fire the laser. The laser wasn't designed to be efficient. The laser was designed to give us as much juice as possible to make this incredible conditions happen, basically, in the laboratory.
So here is when I believe that there is an opportunity for industry working together with academia and define a roadmap of making this laser or multitude amount of lasers being as efficient as possible. What is your take on this?
You're exactly right. This is a wonderful opportunity for the community working with industry, because the national labs and the universities don't make lasers. They assemble the parts, right? They design a laser, so they need industry hand in hand to work with them on this stuff. Exactly what you said. And it's going to be, again, many lasers. What I think you'll see a lot of effort in the near term of let's find the building block. What happened with NIF, we built one beam of NIF. It was called Beamlet, to demonstrate that we could build 192 lasers. But we built the first one to do, as a prototype. And that was so critical, to be able to say, all right, now we can build 192. And I think you'll see the same thing over the next couple of years. You'll see people saying, build me a prototype, and whether it's a 5,000 lasers or, 100 lasers, show me a prototype. And that's going to be reparatable, that will operate, at 10 hertz, typically is what people talk about, a few to 10 hertz. Show me that it can be efficient and that I can have a projection of cost in the future that will be affordable. I think that those things will clearly be something that we will all be doing over the next several years.
And we are talking, of course, about the laser part. But do you see also opportunities on the detector side? I mean, at the end of the day, we need to detect part of the light that is emitted, but also part of the energy that is captured. What opportunities do you see in that respect?
It's a very good point. So detectors are very, very important. I mean, the advances that was made with NIF was partly because of the development of advanced diagnostics to be able to measure what goes on in the physics experiment. And so optical detectors, looking at light, from hundreds of kilovolt of X-rays all the way down to, into the fundamental, to the 1 micron and such, or UV. That's going to be done. We have to learn to keep them in radiation environments, because the neutrons, the radiation from fusion has to be able to, will come, and we have to still have detectors that can survive and make measurements in this very radiation-rich environment. So these enormous opportunities also in detectors that have the spatial and temporal resolution and radiation hardness necessary to be able to make the measurement. So absolutely right. And you'll see that happening, a lot of expertise and desire to go into those things too.
Let's dream away. What is your preferred future?
My hope is that before I leave this planet, to see a fusion pilot plant that shows the future will be fusion energy, because fusion, eventually the world needs clean, carbon-free energy that's accessible to everybody. Not fuels at a few places in the world, but everyone can have access to it. And my hope is that I'll be able to see in my lifetime that to take place. So my children and grandchildren will have lives where energy is something that everyone has, and we don't fight wars over, we don't fight crazy politics over. It's just something that makes the world a better place. That's what I like. That's my dream.
How close are we? If I can ask you, I'm sorry for being so naive, but I would like to know, how close are we from having fusion as commercially available, viable, clean energy source?
That's a very good question. One of the jokes about fusion, it's a future energy source and always will be. Well, that's been a joke for a long time. And so my hope is the following: both with government money, but also the private sector. There's a lot of people who are interested in investing now in fusion research. And when science is done, engineers can make miracles happen. Look at the Webb telescope, right? There's a miracle. I mean, look at that. So engineers can make miracles happen when money is available and the mission is there. So my hope is that over the next several decades, it's because again, this is not John Kennedy once said, "On Earth, God's work must truly be our own." Fusion is how nature makes energy. And make it here on Earth is a daunting challenge, but it's one that will be forever remembered and make the planet a better place. So my hope is that, answer your question, I think the science will continue to advance over this decade. The 20s, we'll see science continue to advance, and the science will begin to show the promise is close. And then once as that happens, as we begin to see investment by the private sector and the government together, engineers will begin to put together fusion plants. I hope we can see a pilot plant in the next decade, wow. and it will begin. It won't be one that will be the ultimate pilot plant, but it will show that all the parts play together. I think that is possible if we have the commitment and persistence and perseverance to make it happen.
So for the industry, there are ways for us to accelerate Mike's preferred future. Of course, Absolutely. Developing the right light source, developing the right beam splitting, providing the right nonlinear crystals, but also providing that to the researchers, but also working together by making sure that from the private sector, there is investment to take that research to the next scale. Mike, this was fantastic. Thank you so much for this great interview. Thank you.
Well, thank you for your interest, and I'm a big fan of Optica. It's a wonderful international society. It brings the world together in ways that I think people could not have imagined years ago. So thank you.
Thank you, Mike Campbell, for that wonderfully clear explanation. And if you want to see more in-depth interviews like this, please click the subscribe button and notification bell on this channel. Until the next interview, onward with Optica.